We can start. So, good afternoon, everyone. We so far discussed that, like how the modeling of uncertainty can be done. So, we discussed that uncertainty can be, modeled with like creating different scenarios with different probabilities. Once scenarios are being created, then we can do the stochastic modeling of the problem, and then we can solve it at the different stages of the uncertainty. Okay, so so far we were only like, the objective was whatever is the expected value of our objective function, whether it is cost, then it is the expected value of the cost should be minimum. If it is profit, then the expected value of profit should be maximum. So this is how we have developed our objective so far. Now some uh, but still, like, if we make decisions out of that, so like how to handle risk or risk management, if I talk about. So with uncertainty, there is always a risk in the decisions, and how we can manage it. So far we were doing it like, let's say whether it is minimization or maximization problem, doesn't matter. So the problem will be like, a minimization of let's say certain expected value over all scenarios. Okay, and some function is there, and that function is like some x values there, some scenario values there, and we are trying to minimize or maximize basically this particular value. And the constants are basically that whatever is the x is, let's say, some constants are defined with this particular set, that x is the like part of the solution space capital X. Okay, so this we wanted to minimize or maximize basically. So if this is cost, then the objective function will be of minimization. If this is the profit value, then we will maximize this particular part. Now, let's say we can calculate or quantify the risk value. Okay, so let's say the risk can be quantified. Okay, and that value is let's say with over all scenarios, the risk value of this over objective function is given by this function, that some risk is there. There is a question, some problems represents min or max or infi or like this. Please explain the significance. Uh, yes, we will talk about that. So if you simply Google it, if we are talking about some uh, continuous problems, then this arc min or infi-min or infi-max or org-max, they are all to same basically. There is no difference. But if you are talking in terms of the different sets, that like if different members are there, then what will be the value of like org min or org max or infi min infi max, they have different meanings. Right now I think I'm not able to come up with a good example to explain these two, but it's for continuous problems, whether it is arg min or a normal minimization, both will result in the same basically uh, outcome. Both are same if we are talking about the continuous problems. Okay, so now the come back to the risk management. So let's say for a fx is basically dependent upon the scenarios, and with each scenario we will have some objective function value f, and the obviously the scenario is with the probability. So multiple, let's say 1,000 scenarios are there, then 1,000 function values will be generated, and they will have some probability. Okay, so for those values we can basically, let's say, obtain some risk. Let's say we have some methods by which we can quantify the risk, and that value is given by RW, that risk function, and it depends upon the function value itself. In that case, the problem which like risk aware problem. So if I like put risk in my model, I will minimize expected value of my function, whatever is the function, which will be in terms of the scenarios, and then the risk value as well. So it is like f of x w, and I will, so it is minimization. So I would add these values that I want to minimize the cost as well as the risk value. If it is maximization, then what I will do is I wanted to maximize my function value, and in that case should minimize my risk value. Okay, now these values are basically like so these different values are contradictory or conflicting objectives. So this is one kind of multi-objective problem. So we can basically place a certain weight here. So let's say like 1 minus some beta here, so weight, and beta weight I can put here. Let's say beta is here, and 1 minus beta is placed here. So depending upon this value of beta, I can say that okay, if beta is 1, then the objective or the actual function fx, expected value of whether cost or profit, that has no significance on the optimization problem, and we are only minimizing the risk value. And if beta is, let's say, 0, then this risk value will be 0, and it will not have any impact on our solution. So we like make some trade-off that okay, this much risk I'm willing to take, and based upon that we sometimes formulate these problems. So let's say like I will put a or here, and or I can like write down maximization of the expected value of the function value. Okay, and subject to x was already defined, and sometimes like so this is a trade-off solution like the above two formulations. Like with this beta value, we have certain you know trade-off between the like whether we want to maximize more the risk value or maximize or optimize the more towards the cost or profit values. But sometimes we can also put it like this, that the whatever is the risk value, it should not be more or less than a particular value. So I can say, let's say, some delta. So this risk value, whatever we have quantified, we can say that the risk value should be less than this particular value. So we can put it like that as well. So these are different ways of putting the different values, or like modeling the risk. And this is how we can, so like here we have added one extra constraint. So this extra constraint represents so extra, I would say, risk constraint. Okay, so this risk constraint I have placed that my risk should be less than some input, user input, that okay, if depending upon the decision maker, he can decide what should be the value of delta. And again, these are basically like multi-objective, where we decide how much weight we are giving to each objective, like whether our actual objective and the risk value. Okay, now how to calculate these risk values. So there are some risk measures. Okay, so there are different risk measures, and using those risk measures we can calculate the value of risk. So one very popular is variance, which we discussed in earlier morning session as well. So very first measure is variance, and I think we can define sigma is basically expectation of, okay, wait, it is nothing but the expectation of uh, mean value minus summation of xi divided by uh, n. Yes, it should be sigma squared, so I'm going there. Variance is sigma squared. Standard deviation is direct, and I think variance is sigma squared only. Yeah. So this is variance I'm naming. So you can call it sigma squared. Doesn't matter. Okay. So what was the formula for variance? I think this summation should come in front, if I'm right. So what is the variance formula? So it is basically mean minus xi divided by n and summation over I, right? Yeah. So this value is basically sigma square, and this part should be squared because we want to have the error in both the directions, whether it is positive and negative, it is variance. So whether it is like, whether it is above higher side or lower side, it should be positive, treated as a positive. So we'll put a square as well. So this is we can calculate. Okay. And or other way around, like, you can also use x minus mu. So the variance I can calculate, like variance of this particular problem is basically the expected values over all the scenarios, and whatever is the x comma w minus expected value of x comma w, okay, and then square of this. So this is the way we can I can write down the above formulation. Both are same. This expected value is basically like, okay, let me change the color. This term is nothing but the mean. Okay, it is weighted sum. So expected value is like weighted sum with all the probabilities of the function. So this is the mean. Then this is x minus mean whole square, and this expected will give you the average value. Like this will provide the average value. So this is how we can write it down. Okay, so this is like one way of doing it. Then one more tool is like, there are others as well, like, some shortfall probability is there, like what is the probability of profit being less than a predefined value. And then one measure is expected shortfall, that for a given probability, let's say like 5% or 10%, what will be the shortage in the profit. So those are the other measures, but the very other, you know popular measures is basically the third is value at risk. Okay. And value at risk is basically defined as VAR. Certain alpha is the confidence which we wanted to have, and it is either the maximization of some value neta, and such that the probabilities over all the scenarios, and where the function value x comma w, if it is less than neta value. Okay. So what is the probability? Okay, wait, this big. thing will go after this. So the probability of profit being less than the predefined neta value, if it is less than or equals to 1 minus alpha, then whatever the neta value which defines, like, should satisfy this particular constraint, that will be the my value at risk. So let's see how the value at risk is, like we can explain the value at risk. So let's say this is the profit curve. Okay, and this is my fxw. Okay, different values, and for each value some probability pi w is given on this particular axis. So this is my uh, profit distribution over the different scenarios. Now, for to calculate variance, basically we have to first of all identify the mean value. So we will identify the mean value. So it is nothing but the expectation, as I discussed earlier. So this mean value will be the expectation of the and all the profits over the probabilities. So that mean value, and then we will calculate, like, there will be different points on this particular graph, and how much is the distance from these particular points. So this is, like, calculating the distance from like different scenarios with that respect to the mean value, and we will square it. Okay, just to keep it positive, and then average it, like expected value of over the w, that will be the variance. Okay, as just I explained here, like, what will be the variance here. Now, conditional value at risk is you have to provide some confidence level, that how much confidence is there in the profit. So let's say if alpha is, let's say, 90%, it means 1 minus 90 will be 10%. Okay, so it is looking at the profit value for which uh, what is the probability of profit being less than some value. Its sigma is some value. Okay, okay. So some as sigma, and the probability should be 10%. So let's talk about the probability. So here the probability will be less. Okay, so certain probability is there, and the entire area gives you the 100% probability. So let's say up to this particular part, this is, let's say, 5% probability. So at this particular part I will obtain some value of fx. So let's say f xw, or I would let me call it f1. Let's say that this is the 1 point. So this f1 will be less than some neta value. Okay, and what can be the maximum value of neta for which the overall probability where the function value is less than neta have the 10% chance. So I will come up to the 10% probability. Okay, so this is the 10% probability up to this particular part from here, and this value is basically the neta value. Okay, and all the fx values, like on this particular curve, these fx values are less than neta, and their probabilities are basically up to the 10%. So the maximum value of neta is this one. So this neta value will be called the value at risk. Okay, so for a, let's say, 10% probability, whatever is the value of fx or the function value, that is our conditional value at risk. That okay, with a particular confidence level, uh, the profit will be, or the uh, overall profit will be this much. Okay, so this is how we can define that. Okay, 10% times, or like with a confidence of 90%, it is 10% time profit will be less than certain value, and that certain value is basically value at risk. Okay, so this is how it is defined. Then the third measure is conditional value at risk. Okay, which is also a popular measure. So it's a conditional value at risk. Conditional value at risk. This is again very interesting, and how it is defined, that this CVAR is defined again with some probability and over X, and it is defined as a maximum value of this neta. Neta is value at risk minus 1 upon 1 minus alpha. So this is like average value of expectation, where maximum uh, neta is there, and whatever is the neta, this value is basically the difference between neta to the function value we are calculating, and whatever is the maximum between this value and 0. Okay, so and the average value will give you the conditional value at risk. And the significance of this, like this is the some mathematical term, but if I talk about the significance, if you look at this value, so let's say some neta is defined, and this neta will be defined with respect to the alpha confidence level. So this particular confidence level, this neta has been defined, and neta minus fx value. So neta minus fx, if fx is on the left hand side of this particular part, okay, so this is, let's say, left side, and this is right side of the neta value. So neta is still not defined. It will be basically outcome of the this solution. So if fx is less than this neta value, then this first term will be positive, and it will be more than 0 value, so that value will be added. Okay, so we will add them. So it's expectation we are calculating, so we will basically uh, add all those values and multiplied with the probability. So it's expectation, so multiplied with the probability as well. If it is on the right side, then you can say that this first term will be negative, and we will get a 0 value on the right hand side. So this expectation is basically uh, and then divided by 1 upon alpha. So 1 upon alpha is like 1 upon 1 minus alpha is like 10%. So if alpha is 95% or 90% confidence, then either 5% or 10% will give you the 1 minus alpha. So this is nothing but the average value of these points. So it is nothing but the average value. Okay, this entire term is the average value, and whatever is the average value, so let's say the average is somewhat here, then the difference between the neta and average, that will give you the the conditional value at risk, that how much losses are there and beyond the value at risk. So value at risk gives a look at only one point. Conditional value at risk, all the points which are that particular and less than that particular value. Okay, so this is how it has been defined. Now uh, how we can model it in our program. So I will try to put first of all like the variance in my model. So we discussed the earlier that renewable self scheduling, where we just so let's consider an example of RE self scheduling. Okay, so in RE self scheduling, we had a objective function of maximization, and that was summation over scenarios pi w, and then summation over t, and then some lambda d t w p dt plus lambda plus t w, and delta plus t w minus lambda minus t w, and delta minus t w. Okay, so we had this summation over this and one summation over this. So this entire function I can just replace this internal term as a fxw. Okay, so I can say this entire function is maximization of summation over w, pi w, and fxw. This is how I can put it like this. and this is nothing but the expectation of fxw. Okay, this is also expectation of the function value with respect to the scenarios. So if you go back and like we explained this part, that our objective function is either minimization or maximization of fxw, then we can calculate the risk value. And once we have obtained this value here, if I want to model with, let's say, with variance, okay, so I will put maximization of this expected value of fxw. So this will be the same objective function which we have used, subject to different constants satisfying the capital X. So those constants will be, like, okay, here we did not consider. Those constants will be these, all of these constants. So these constants will define the solution space. And once we put all of these constants, we will add one more constant, which is of the variance value. And that can be, like, placed as a risk value less than some. Uh, okay, wait. Yeah. So this is over all the conditions, and we can put it like, maximization, minimization of some beta, and the risk value was variance. And variance we have defined earlier that it is the expectation of, so expectation I would place with a summation omega equals to 1 to number of omega and pi omega. So this is how, like, the same analogy we can place from here, that this part we have replaced with, this particular part we have replaced with the expectation. So as we have defined the variance, like, expectation of, so this will give me the expectation. Then what is the expectation? Expectation will be fx. Okay, f x w minus, again, expectation of those values, which is like mean. So I will call it expectation of x w and the square of this. So in general, I can write it down like maximization of summation over w pi w, and then basically summation over t, let's say lambda d t w p d t plus one term minus another term. So this, like, this is the first term and this is the second term, so I'm not writing them down again. So this first term is my objective function minus beta. Then I have to place the variance in the objective function. So variance will be expectation of the this thing. So I will put a summation over omega and pi omega. Okay, and then I have to put a square. So what is the function value? So function value is nothing but the summation over t lambda tt w pdt plus first term minus second term. So this is what we have as a fxw minus expected value of the first term. So this is, I will repeat the same term here. So this is nothing but the summation over w pi w, and then summation over t and lambda d pd tw t plus first term minus second term. Okay, so this is over time, then over this, and then entire term whole square. Okay, so this is how it will look like, and subject to the constants, which are the same constants. We had those constants like, delta plus minus. So I'm not putting that tw, let's say, and this is minus tw equals to pf TW minus PDT, some limits on delta plus and some limits on delta minus and some limits on PDT as well. Okay, so that we have already discussed that what will be these limits. So this is how I can put the entire formulation in terms of variance, and I can minimize the variance along with maximization of my profit. So this is how we can solve it. Is there any doubt? Okay, so I have provided you, like what how the problem will look like with respect to the variance minimization. Similarly, like we have discussed that in generalized way we can put it like this, like some objective function and risk value. This risk value can be value at risk. This risk value can be condition value at risk, and you can basically use other values here as well. Uh, but one thing which we have to make sure that they should like so one risk measure is shortfall probability, and that probability is not function like profit. So we have to normalize sometimes these like different objectives. So there are like first objective is profit, second is, let's say, the if I use the risk measure as a probability, so the second cannot be like profit cannot be added with the probability. So you have to normalize it, and otherwise put it other way around, like as a constraint as well. So instead of objective part, we can put that, okay, that the shortfall probability should not be less than particular value. So either we can place it like this, or the same part we can also, the another formulation is we can also plate like put it like this, like maximization of uh, summation over w, pi w was there, summation over t, lambda d tw pdt plus first term minus second term. Okay, so this is the time and this is the expected value subject to all conditions which we have discussed earlier, and I can place the this particular term in the constraint as well. Okay, so that term will be, okay, let me copy it, will be easier. So okay, so control C, and let me place it here. Okay, so we can like calculate the variance and then put the condition over here that this variance should be less than or equals to some predefined value. So this is also how we can model it. Okay, so it depends like how you want to model a particular problem. Generally, if I am talking for the variance point of view, I would try to keep that in the objective function so that all the constraints should be linear. Okay, any doubts here? Uh, about that, like what are the how we can calculate like chance constant optimization and the robust optimization. I have asked Dr. Deep Kiran to explain that in detail. He will take that session. Okay, so how to handle like uncertainties, or what is robust optimization. Okay, so we will talk about that. I've just gave you like very fundamental of like how we can handle that risk. Then let's add a new section. So, so let's talk about particle PSO method. Okay. So PSO is basically a population-based optimization technique, and it basically inherent the features from the you know a swarm of species and how they react. Okay, so like how birds are flocking and fishes, how fishes are they swim in a group, and how the social behavior works, even the social behavior of the humans as well. Okay, so without going into like much explanation, you can like read about particles optimization on like Wikipedia itself. So the natural evolution and everything, you can find it there. I will directly go to two very important formulas. One is vi k plus 1 and equals to some inertia, and vi k plus c1 r1 and pi minus xi k, and then plus c2 r2 and g minus xi k. Okay, so this is one formula, and this is generally call it velocity update. We call it velocity update. Another formula is position update. So position update is simple. Xi k plus 1 will be whatever is the current x plus velocity of the k plus 1. So these are the two formulas PSO function utilizes. Now, what is the meaning of each and every term, and what is the significance? I wanted to discuss about that because you must have seen these formulas, and I think you are also aware like how to use them. But let's talk about uh, how we can, what is the significance of these. So let's say this was some function which we discussed earlier as well. Okay, so this is the function value fx, and this is the variable value x, and it's a single variable problem. And we can see that this is our global optimization which we want to achieve. And let's say we wanted to solve it for maximization problem. So in particle form optimization, we create different particles, okay, of the swarm, and they will be created randomly again. Just like GA, we will create some random initial candidates. So let's say I have created one candidate here, one candidate there, another candidate here, another candidate, let's say this one, somewhat here, and the third one is this particular position. So let's say we have created six number of initial candidates. Let me give them numbers as well. So 1, 2, 3, 4, 5, and 6. Okay. So these candidates are basically has been created, and you can see the maximum value or the best from the maximization point of view. Candidate 3 is at the optimal point so far. Okay, and candidate 6 is at minimum point. Now, if I want, okay, let's consider another side here. So Another part is, let's say, a single peak value, and this is my optimal point, and let's say this is my starting point. So this is x naught, this is x star. So simple optimization problem is basically like, no, we wanted to move this particular value in the direction of this objective function. So we will basically have some step size, and the step size will be r and x. So this will be the one step, then some r and x another step, some r and x another step, and we will move it up to this part. And this is how, like, some step will be added to the initial solution, and until the objective function like, start keep on changing very much, and the difference between this, like, x naught and x1, then let's say x3, x4, and finally like x5, let's say. Okay, so the difference between x1 and x naught, so here I can say like x1 is x naught plus some alpha, and I would use like some step size, so like x1 and x naught. So let's say 2 points was already created, and then I will add them up, and whatever is the difference, the deviation will increase further the value of x values. Okay, so x naught, x1, x2 will be like this. Okay, so the 2 points has been created, and we can come up with the another x2, x3, and x4. So this gives the, like, the direction whether we are moving away. So if this value is positive, it means the new value is better than the previous value. Okay, and we basically not exactly f, it is, I think, function of x, function at these values, and then this will give us the step size that, okay, you are whether moving in the direct direction or the opposite direction. So the particles optimization also works in the similar fashion, that this point 1 should move towards the uh, 3. Okay, so it should be updated first of all. Okay, that this point should move, uh, if it is maximization, it should move in this particular direction. Okay, and it should reach up to this particular part. The point number 2 will try to move the objective function in this direction, that, okay, if it is moving other way around, the function value will be decreasing. Okay, so this function is decreasing, but if this second particle moves upward direction, it will again go to the more objective value. So its function value, or the, objective function value, is improving if they move in this particular direction. So I will mark the arrows that how they are going to move if they wants basically, some update in their objective function value. So this is the movement of their update. Now how this update is being decided. So initially we will have certain initial, like some velocity, that, okay, the first step which, let's say, this one will take, will be based upon the some initial velocity. So we will provide one step. If this one step is better, then it will start moving in this direction. If this is not better, like, let's say, the because of the initial velocity, if the new point came out to be less, then the new velocity and new update will be in opposite direction, so that, it start moving on the other way around. That is basically, if you see here. Okay, so let me draw this particular part again, this much. So initially, let's say we were here, and due to some initially no personal will in factor was there. So, and let's say with some initial velocity, we were able to, like, from 0 to 1 we have moved. Okay, now how the PSO works? It works basically with the own experience. So this particular segment at the second part is basically, like personal experience, and the personal experience is, this is P is the personal best. This is current position. This is also current position. This G is uh, group best, group based or global best. These are some weights on this particular one. This is the initial velocity, and subsequent this velocity will be used, and this is like inertia of that particular velocity. So let's say initially the velocity was in this particular direction, opposite direction, because we don't know whether the solution will be upside or downside. So initial velocity moved point from 0 to 1. Now if I look at these 2 points, uh, this is best option. So this is basically P best, personal best. This is the current position X. Now if I just look at the first two terms, some inertia will be there. So that inertia will try to push this particular point, which is at one current position, in the opposite direction, because the initial inertia or initial velocity was in downward side. But the second term, which is like personal best minus current best. So if the personal best is 0, so 0 minus current position will move in the opposite direction, because it will come something else. So it will move it in the this particular direction, depending upon the let's say the initial velocity still dominates as compared to the distance between the personal best and the current position. Maybe the next point is at moves to this particular point. So let's say this is the second point, and this becomes the next current position. Still, the velocity, initial velocity, or the inertia on the velocity will try to move it on downside. But now the personal best is still 0. Okay, so this point will try to move in this particular direction. So this will then the distance between the personal best and current position will be more, and it will dominate the inertial velocity, and then it will start moving like from this particular point to maybe this particular point, and then so on. It will start keep on moving towards the optimal point, and it will try to reach this first peak, which is here. Okay, so this first solution will try to reach here, second solution will also try to reach on the first peak. Now, can you, by looking at this particular, function, we know that this first peak is not the optimal solution. The optimal solution will be at the second peak. So we cannot move our solution from, if I just incorporate the first and second terms, it will stuck, these both of these particle will stuck at this particular position. Third particle will move to the global best solution, or whichever is the the optimal solution. This particle will also move to the global best solution. Fifth will stuck at the current position because it is the peak. Six will also move towards the third peak. Okay, but we don't want that. We want all of these solutions to basically move from here to here. Okay, so that's why a third velocity segment has also been added. This segment is basically looking at the distance from the group best. So group best is current right now third number particle. So it will try to move this first particle towards the 3, second particle also towards the 3, and instead of moving this particular point in this particular direction, it may basically move it in this direction as well. And everything depends upon how much distance they are basically away from the group best. Okay, and at the end, all of these particles will try to move towards the global peak. So they are basically moving here. Even this fifth particle will also try to move towards the global peak. The thing is, all of them, they need not to move, or basically completely move at the global peak. So as we are creating a population, we are creating a number of particles scattered over the entire solution space. So this line is basically where our solution will be. So these points will be scattered over entire solution space, and then they will try to move towards their local optima. So these, the first and third peak is local optima. So they will try to move towards that point. Once this first point has been moved to the local optima point, then the personal best and the current position update will become zero because it has been already reached to the local optima. So this personal update will become zero, and then the global update, this third term in the velocity, will enforce, and it will try to move this point towards the second peak, which is the global optima solution. Okay, so this is the significance of these. The first term is basically like inertia of the velocity, that if you are moving in this particular direction, let's say in one direction, the velocity would basically movement we will like to have is in the same direction. But if the distance, because of this initial velocity, if this distance is increasing, it will overcome the initial velocity and basically dominate the initial velocity. Now, why basically, like, if we are looking at these values, generally we do not keep this omega value too much high. If we keep it too much high, the personal best or update because of the personal best and update because of the global best will become redundant. So we do not keep this omega value very high. Any doubts in PSO, like, so far which we have discussed? This is the like significance. Now let's talk about the different parameters. Generally, this omega is basically in PSO how variations are made, like advanced PSO and improved PSO. So like how we are updating our solution, those things basically define the advancement in the PSO. The very fundamental is basically what I have explained to you. Now sometimes, like I want first of all, like exploring the entire solution space. So let me give you another example. Okay, let's first look at the values. So generally we keep it this kind of values. C1 is generally like up to 2, or we try to keep it like between 1 to 2 values. Same for the C2 as well, and R1 R2 are some random value between 0 and 1. Okay, so this is how we solve it. Now let's consider another example, and just try to visualize the things, otherwise with the example it is very difficult. So let's say weird function is this, let's okay, so let's say this is a function. Now the particles which I have created initially, let's assume those particles are here, here, and here. Okay, let's say these are the 4 particles which we have created. Now if you look at the particle number 1, 2, 3, and 4, so the G best is basically third particle. Okay, so the global best will try to move this second uh, particle towards this particular point. And if this point is basically let's say, instead of, okay, let me change this one, erase second, and let's make the second particle this particular point. Okay, so let's say this is the second particle. If this is the second particle, and let's say the inertia was also, initial velocity was also in this direction, and as g best is also in this direction, so this particle will start moving towards the 3. Okay, if this particle start moving towards the 3, then and some initial velocity, okay, let's keep it like this, that the initial velocity was here, was in this direction, but we are moving, like towards the 3, and second update was here, but because of the second update the distance is very less, so it will again move it towards the 3. And if it overcomes this barrier of this valley, and if it moves here, then it will continue move towards the this particular peak, and the solution will be basically converged here for these second and third particles. They will never go this particular position, which is the global optimal solution. So the advancements or improvements are basically, like we can define these updates, and maybe dynamically with some iterations. So you know these values are basically like, so first solution should be basically like, whatever the randomly initial points we have created, we should look for the solutions nearby to those points only. Okay, so just like, in this particular example, uh, the impact of this personal or basically g best, basically this impact of g best should not affect my solution initially. So this velocity parameter inertia should be very high initially, that okay, I'm looking at the different solutions nearby this particular point. Okay, so whatever is the initial point, I will explore the entire space whether a optimal value is present there or not. Once I have obtained these values, then I will compare, basically use the information of the entire group, and entire group is some g best will come into picture, and if some other particles are at a higher positions, then I should move towards that particular position, until unless I should locally explore the entire solution space. So it's basically like, exploring the entire space and then exploiting that, okay, fine tuning to get the maximum output. So those approaches should be there. So instead of, like keeping a fixed w, I can have a dynamic w, that initially the w value will be very high, and then over the iterations I will start reducing this w, and I will have more significance of the uh, group information. So this is like, cognitive knowledge, and this is social knowledge. Okay, so I will try to have impact of social knowledge more later on, when I want refined solution, more accurate solution. Initially I wanted to explore the entire solution space, so I will keep the frequency or the basically inertial velocity to dominate. So those kind of, advancements and improvements are, different, again a lot of variations are available depending upon like how you are looking at a particular problem. Okay, so initially I would like to explore everything, so I would keep, one improvement or advancement is, instead of in fixed value of w, we can basically change these values sometimes. So one best thing about the PSO is, we can work on real values. Okay, all of these are, like x can be a real value, instead of like, in genetic algorithm we used binary, and then some modified versions are also on a real coded G as well. So this is how we are, and then this velocity will be added to get the position update. So PSO again, it's like, very easy to understand. It's clearly like, explain that how the personal knowledge and the global knowledge should basically affect our solution, and all of the particles should move towards the global optimal solution. Okay, so I hope I am able to answer you. So there are many improvements and many advancements on the PSO as well, just like the GA. Okay. Sometimes the problems, like I've discussed you that problems are not continuous. they have integer variables. So we can have a hybrid approach of GA and PSO as well. What we can do is we can model the integer variables in the GA, because GA is very good whether like within 0 and 1s, that whether you want to keep a particular value on or off. Okay, so we can use GA to handle the integer part, and then we can use the PSO to handle the continuous part as well. Sometimes we can do a hybrid of like the nature inspired as well as the conventional method. So what happens that like some of the variables are there, or some of the constraints are making the entire problem non-convex. So if we can like assume a certain value of those variables with the help of either nature inspired like G or PSO, so those particles will have a particular initial value of those particular variables. Once those variables has been defined, then the rest of the problem becomes convex, and we can easily solve the optimal point for those remaining convex problem, and then update the integer parts at the certain variables again with the like this GL PSO. And so it's a hybrid approaches can also be used. So you have to find out the proper coupling, that which variable is providing a coupling between the different equations. Any doubts so far? So next thing is like we are living in era of these toolboxes which can provide you different codes. Okay, so why not use them? What is your opinion about them? Should we use chat GPT or like grok and all of these tools to write our codes? If one of you used these tools to write the code. uh, okay, it removes the pleasure of coding, but look, we can I would say we can and we should use these codes, like just we don't want to waste time. So but whatever the code these tools are providing, they may be wrong. To be very honest, these codes will have lot of error, and you must have, I think, if you are using it, you must have faced it that the results are not exactly like what we wanted them to be. So I also tried it yesterday. I asked ChatGPT to write a genetic algorithm code for me, genetic algorithm code for me with the help of like ACO for ACOPF problem. So yes, it provided me a code, and the objective function, the fitness value was obviously the post was included in the objective function to calculate the fitness of a particular chromosome, and all the different constraints which we have, if those constraints are not being satisfied, it has been included as a penalty term. What it did is the chat GPT did is like instead of like we used to write down that equation like pg minus pd equals to power flow, and power flow formula was vi vj yij cos theta ij minus delta j plus delta I. So this was the power flow formula for our ACOPF. It provided me the formula which is pg minus pd equals to vi vj. Now how the power can be equal to the voltages. So, but it gave me the code. I ran run that particular code. It gave me some answer, not optimal one, but some answer. And but I was sure that okay, that code is not correct, because when while going through it, I was able to identify the issue. So I again asked ChatGPT that why you are making this mistake. This formula should not be this. Then again the answer was yes, you are right. Okay, no, I specifically provided the entire formulation to the ChatGPT that this is the formulation and you have to give me the code for this particular formulation. But it assumed VIVJ only. Okay, so then it assumed, you said that yes, you pointed it rightly. I made a mistake, and then it gave me something else, which was also weird. Okay, and that code never gave me any answer. But again, here we are, and I have again used ChatGPT, and let's see how much good it provided me. So we have a code for economic load dispatch. This time a quite simpler problem. Okay, and for PSO. So this is the code which I have not written. I just provided the these input set. Okay, so that these are my input, and rest of the code is basically written with the help of ChatGPT. So I have not I'm not sure whether it is right or wrong. Let me run it, and let's see what we get. So it is solving. Okay, so some best cost is there, and some, yes, graph is also there, that it is converging very fast. It does not need 400 number of iterations, because the solution is converging within, I think, less than 50 iterations. So let me change the number of generation, which is 400 to, let's say, 100, and run it again. So this is the convergence graph I'm getting. And if you look at the outcomes, the powers are 433, 320, and 112. Then I checked it with the book, that what are the outcomes, because I gave it the same example which we have in our book. And so let me see if I'm it taken the same input parameter. So it is 7.28597, and then it is zero point 0 this 0.388 and 960. Okay. Yes. So the data is perfectly fine, and the outcome which we are getting is roughly around, first generation is 433, and the solution from the book is very close to it. So the first generation is perfectly fine. It is 433.94, but the second generation, the solution which we are getting in the book is basically 300 something, and we are getting here is 320. So we can say that we are not getting exact answer in this particular part. Now let's see, if I remove the complexity of the losses, then what will be the answer. So what I can do is, I can make this b equals to zeros and a 3 by 3 matrix. Okay, so like whatever the values I have provided here, they will be gone, and the demand is 850 megawatts, and in this particular as well, I think we have the same demand of 850. Okay, let me run this time, and let's see what is the solution. So it has been converged, and the solution is coming out 493, and without losses the solution is quite straightforward, and it should come out 393, 334, and 122. But we are getting a very weird result here. So let me again solve it. Now it is somewhat closer to what is available in the book, or which is actually optimal solution, because we know that it's a convex problem and whatever solution is provided in the book is perfectly fine. Now, how we can improve this particular solution? So the population size is, let's say, 100. Let's make it 50. Let me increase the generations, number of iterations, and let's see. So it is converging very fast, and the solution is very weird again. Okay, so we are not able to converge it. Now let's increase the population that may end up close to our optimal solution. So let's see what is the answer this time. So it is 393. Instead of 334, it is 329, and 122 is 126. So it is somewhat closer to the our answer in the book. If I run it with 1000 iterations, maybe it will give me the answer. And the solution is again weird. Okay. So the point is, we are randomly initializing certain values of P1, P2, P3 in this particular part, that these are basically some random values of P1, P2, and P3, and based upon that, we are basically solving this particular problem and using this particular code. So maybe there is a mistake in the code. Okay, I have not like explored it, but the solution which we are getting is always different and random, and that is because, like, the initial solution, if that solution are the particles which we have created initially, if they are far away from the our optimal point, as I explained here, uh, stop and share again. So, like, this case is there. So if the particles are nowhere near to this in this particular curvature where the maximum peak is there, you may not get the solution. Okay, and so this happens. Now we have to run it multiple times to get the solution. Okay, so this is what we have been, like, tried to use it. Now let's see how the we can handle this particular problem. So you can see that we are using uh, three, like, different variables, and each particle is basically we are creating the population size and number of like particle positions at certain velocities, and then we are creating a certain initial value. So if I look at this x values, it will give me the, like, okay, 500 by 3, and let me see what values it is creating. So okay, some initial zero values has been created. So three variables are there. Now the entire like solution, it is, if I convert that entire problem into single variable problem, then I think we will have better solution. And we have used or basically solved the single variable problem as well. Like the lambda iteration method, we only considered one variable lambda, and we are updating that lambda, and with that particular lambda we are getting p1, p2, p3, and depending upon the value of p1, p2, p3, we are fixing those limits, and then getting the solution over and over. Okay. So instead of, like, using p1, p2, p3 as a particle, within the particle, we can simply keep lambda within the particle, that okay, this is the only single variable problem in terms of lambda, and then we try to solve it for that. Okay, so if the dimension is reduced, it will give you the better results. Now let's say, now what is the effect of these? Let's say instead of 0.3, if I keep it 0.4, okay, and then run it. If I get the correct answer this time, if the inertia on the um, initial velocity is very less, still the answer is very vague. And so let's keep reduce this one. Let's say keep it 1.2 and then run it. Still we are getting some weird solutions. So we have to look for different times. Yes, yes, that is very much true that random functions are there. The R1 and R2 are random values, and the solution will be different. But over the iterations, we are running it for 1,000 iterations. So it should converge to the optimal solution. Okay, and I'm not expecting the solution to be very close to the actual values, but I'm expecting it to be, as close as possible. That need not to be exactly same, but should be as close as possible. But so far, okay, let me create many variables, and how it is creating those variables, that will also depend. So it is p random and some values. So let me see how the different x has been created. So some different values has been created between the maximum and minimum limit, and if I run it continuously, I will get some different solution. This time, like the number of population is basically higher, and let's see whether we will get the solution or not. Okay, so it will take time. Now, is there any doubt from you? This is somewhat closer. So, like if I run it for more number of iterations, the solution we are getting is very close to the optimal solution. Okay, so you will never get the perfectly optimal solution like the one which we have obtained with the classical methods. Okay, but again it's a trade-off. Like if you look at this particular solution, it is coming out 392.8, which is 393, and the exact solution is 390.2. So maybe if I increase the number of iterations, it may go towards the more optimal solution. But you can see that these values are still decreasing. Okay, so the best like the solution, it is still keep on decreasing up to the fourth decimal place. And if I increase the tolerance, like how much the tolerance should be, and instead of number of iterations, if we increase the tolerance, maybe we get a good answer. So I will share this code as well. It's like it's not mine at all, and I won't mind. So what is the takeaway from here? what are the takeaways from here? Like, why when I reduced the C2 value, which is basically associated with the global best. So some initial population are basically particles has been identified, and those obviously some of them will have maximum fitness and minimum cost basically. So the all the solution basically that will try to move towards that particular point, and that particular point will not have any other way, like moving towards some other position, because um, the point which is best among the initial solution is not basically like not able to move towards the uh, global optimal solution, because the weightage which we have provided is less. So let's say if the inertia is very high and we are not moving the this particular value, like the global best value very less, and if I run it again with the less number of population and less number of let's say iterations, maybe we will get some different solution, and it has been converged solved very fast, and relatively like the values are different, but let's say 5 and 5, keep both the weights equal and inertia weight very high, then we will get some different solution. Okay, so the weird solutions are coming, so we have to tune these parameters, and that is a very difficult process as well. Like tuning the parameters, like what should be the better values of W, C1 and C2, and these also basically vary with respect to the size of the problem and nature of the problem. So there is no single answer of like what values we should keep of these parameters, what should be the population size or the ideal population size, and what should be the iteration size. So all of these are basically there is no single answer to those questions. Okay, so sometimes like the initial solution is very close, it may give you the answer. Let me Okay, let's play with it. So we have created this particular x, and let me create x which is 1 comma all three values are equals to, let me give it the exact answer. What happens then? 334.6 comma 122.2. Okay, so this is like the first particle I have provided the exact value, and let's run it. And I don't think so we need these many iterations or population, and let me run it. Okay, it is perfectly converging. Okay, so we can easily see that the values will remain same, because that is the best optimal solution and we have provided it. And throughout the iterations you can see, like iteration 20, 40, 60, the optimal value is the same, because no other particles are moving towards the other point. And let's see where is the other particles. So we have created x and we have updated x, and let's see what is the current value of x in this particular particle. So these are the 50 particles. So this is 393 and 334, the initial the best solution, which was we provided it brute force way. And all of these solutions are basically trying to move towards it. And okay, let's plot the x values as well. Yeah, so plot coal history and these values grid on, and let me plot. Okay, so this is my for loop, and I can, let's say, output uh, whatever is the iteration. Iteration is one iteration. Okay, we have used iter iteration comma one. Okay, let me plot only p1. Okay, first of all, equals to x, capital X, and whatever is the second particle, its first value I am going to plot. Okay, so this is it, and once I have this, I will plot it op comma 1 2 iteration max. I think that is the term, right? Max underscore iteration. So it is max underscore iteration. Well, let's see. Yeah, something. This should be on the x-axis, and yes. So initially, you can see that the initial value was roughly around 420, and our optimal solution is 393. So this is basically like no particle is moving and trying to converge towards the 393 value. So you can let me plot a line as well. So let's say 393.2 multiplied once and 1 comma max underscore iteration and 1 underscore max underscore iteration. Okay, let me see. Okay, so this is the 393. So now we are getting some other solution here. If I run it again, it will try to convert. So initially it started with the initial value of 280 and trying to convert or that particular value of 393. So yes, we are able to learn. Like you can see that each variable is and the particles are basically trying to move towards the global optimal solution, which is quite visible from this particular convergence of a single variable, which I have used from a single particle only. Okay. So, so the trade-off between value of parameters and accuracy. Yes. So sometimes like solution is very difficult from the conventional. Then we will go with the heuristics, and it depends upon like which kind of problem we are trying to solve. So let's say if DCOPF I'm talking about or ACOPF, I need that solution very fast to know the entire state of the system. Okay, and in that case, I cannot wait on the GA or PSO. Instead of that, like ACOPF is more accurate, but we have some approximations and come up with the DCOPF problem, and we are okay with DCOPF because even the GA PSO, which can solve for the global optimal, but it is not necessarily will give you the best solution. Okay, so the trade-off is always there, and it's best if you can relax the like the initial problem and some assumptions and some relaxation techniques to make it linear, or at least like try to make it convex uh, by some assumptions, like making some variables fixed and solving those variables separately, and other problems like converting it into sub problems as well. So this is the way by which you can get the optimal solution. So let's say like some improved PSO, and let's discuss about it. So what we can do is we can define with each iteration some x inertia value as well. So far we have assumed some inertia which was 0.9. I can keep it like this is the maximum value of inertia, and then it can be some minimum value of inertia is 0.4. Okay, so if this is the inertia, then for each iteration I can calculate the new inertia. So here we are using some lambda and the penalty function, the cost function, and some velocity is needed here w. So I can change that velocity, and in the very first part I can put that w was equals to uh, w max minus. Yeah, so I purposefully gave the initial values as optimal value and see whether it is diverging. But yes, with the giving the exact optimal value, it was able to. The solution was kept on the same value, and it was does not diverge from that particular part. Let's talk about the dynamic inertia weight. Some improvement in the existing PSO, and we can have like the iteration, and okay, let me put it in the brackets. So we have some iteration divided by maximum iterations, okay, and then multiplied with the w max minus w min. Okay, so you can see with the help of this particular formula we are changing the inertia values. Okay, here and let me remove this one. So control R. So now this initialization of the exact optimal values I have removed, and let's try to solve it. So this part is very away, far away, and the global optimal solution is also not correct, but I can increase the population size, and let's say in 1,000 iteration whether it is able to solve or not. So yeah, it is not able to solve at least. Okay, so it's still the answers are very weird, and they depends upon the different initial values again. This time the solution is much closer as compared to, like, if you can see 390 is 401. So what we have done this time are the different is basically I have used the inertia values in the velocity instead of the fixed value. I kept it that the inertia should be some like defined like this. Okay, so initially the iteration will be 1. So if iteration will be 1, the inertia value will be, okay, let me use my notepad. Very good question. How to, so the very question is how to compete with people who use chat GPT while we choose not to. Yanga, nobody is stopping you to use chat GPT. Let me tell you one thing. One very important thing is these tools are there. We should use them. They are there. That okay. We should use these tools for our like research purpose and for our teaching as well. Like many of you are faculty in different institutions, so for teaching purpose as well, and they can provide you like crystal clear notes, like what to cover and what not to cover. Okay, and what will be the flow. But the issue is we should know the fundamentals of whatever we are trying to solve. and once we have the fundamentals, we can easily identify the the solution which has been provided by chat gpt or other these kind of tools. um, what are the issues there? And if you simply use whatever the code provided by chat gpt, it will not give you any answer, and the solution will not be you will not get any better solution. You have to run it multiple times, and maybe if you are lucky enough, you will get some answer. And as I told you earlier as well, like it gave me very weird equation for the power mismatch, which was not correct at all. And when I mentioned it, it accepted ChatGPT that okay, it was a mistake, but it still gave me the same equation. So obviously we have to use our mind. So that is the part we choose not to from your question. And so I would request that okay, you should use them, but use your brain as well. Okay, हम बोलते हैं ना नकल नकल में भी अकल की जरूरत होती है, तो we are coping it that, but we should use our brain as in PSO. We were that the dynamic weight, basically the omega is defined like this: omega max minus the current iteration upon the maximum iterations allowed, and then omega max minus omega min. Okay, so we use like this is, let's say, 0.9. Let's say this is the first iteration and we are using 1000 iterations, then it is 0.9 minus 0.4. So the initial omega is very less. So this difference is basically how much? 0.5 divided by 1000. So roughly around 0.9 itself. Okay, so the initial omega will be very high, and as I explained you, I would like to explore the entire solution space initially. So I would like to keep this value and like this inertia value very high in the initial part of the iteration. So the omega in the very first iteration will be 0.9. But if I look at the omega in the 1000 number iteration, it will become 0.9 minus 1000 divided by 1000 and 0.9 minus 0.4, and that will be basically 0.4, so which is omega minimum. Okay, so this is the minimum value. So at the end the inertia will reduce. So this is how I can basically update the initial weight. And what other attributes we can include is basically we can play with the c values as well. Similarly, why not change these coefficients as well? Okay, and let's change the velocity, initial velocity, to the very high value. Instead of 50, let's say 100 and 100, and let's see how the results are changing. Yep. Some it has been converging, but not up to the exact value. So you can play with this particular code. You can define different values, okay, and obtain different solutions. Here, what I have seen is basically let's keep it 8. Then I think it will give you the answer, because still we need some inertia to explore the entire solution space as compared to the. So like you can see, this red line is our optimal solution, and it is deviating on this particular solution. So maybe after more number of iterations it will converge. Okay, so no, I'm not providing any nptel course, but these recordings will be available on YouTube, so you can use them. And maybe like I will float the same course next year as well. Next year means like next financial year as well. and I will try to cover more new things in that particular course as well. Okay, so if you have any doubt, have you tried to write your own code with the help of the MATLAB tools which I have provided you, like this fmincon and quadro to solve ACOPF problem, and so to solve some other problems which maybe you are working on. So if you have any issues, you can like ask me. We can discuss those as well. Not in the class, obviously. You can ask me privately over email if you are any facing any issue. So I will share this code with you. And is there anything which I want to discuss? Is PSO is fine. If you have any doubts in like like how to model the risk parameters, you can ask them. Okay, let's see if I have an example to obtain the different values of, like what will be the values of the variance and all. So yeah, I have one very good example for the conditional value at risk. I think I have to consider that because variance is quite easy to understand, but the conditional value at risk is a bit difficult. So I'm still waiting for if you have any doubts, we can discuss those doubts. Risk measure is also considered from PDF. PDF, do you mean a probability distribution function? Yeah. So the answer is yes or no, both. Okay. So the risk measure we are looking at is basically whatever is the function value. The risk measure is not from the like the probability distribution function of the input uncertainty. It is basically the uncertainty in the output, and output we are looking at the profit value or the cost value. So whatever is the probability of the output, from those output values we can calculate the risk measures. Okay. Now, one way of calculating the risk measure is solve, do not solve for the variance initially, and just simply solve the entire problem, and for each scenario separately. So if 1,000 scenarios are there, solve this particular problem 1,000 times, you will get 1,000 profit values. Okay. And then those profit values are for scenarios, so each scenario has certain probability, so each profit value will have certain probability. So let's say, like if I simply calculate what is the risk, or the risk measures, like what is the variance, what is the value at risk, I can directly get it from the PDF of the our function, whether it is cost or profit. But if I say that I want to minimize the risk value, so if the risk value is part of my objective function now, or just like this particular constant, which is like the risk value should be less than this delta value, like user input, then uh, for this particular problem, this entire risk value will be equals to delta, because most of the times the objectives are conflicting, and to get a maximum profit, uh, they will try to utilize the entire variability of the uncertain input parameters, and they will keep this risk value equals to delta and provide that solution for which the risk is either less than delta, or most of the time if the conflicting objectives are there, they will fix it to the delta value, and then what will be the optimal solution. Okay. So if the risk values are part of our optimal problem, then we cannot measure from the PDF. But if risk value is not part of my optimization program, like let's say if this last constant is not there, then the above formulation is basically like for different scenarios I am solving this particular problem. And let me give you example, like I have certain example that let's say some scenario is there, some profit is calculated, and let's say certain probabilities are there of those scenarios. So let's consider 10 number of scenarios. Okay, so let's say there are 10 scenarios, and instead of like having multiple probabilities, as you have this much, please consider explaining Monte Carlo simulation. Monte Carlo simulation is very simple. Okay, what it does is it evaluate all the possible scenarios and try to solve the problem. So okay, what is Monte Carlo simulation? Let's say this is the formulation and this is risk constant. Okay, to cover it in very simple words, what I will do is I will remove this function and I can convert this into maximization of summation over t lambda d t w p d t plus first term and let's say second term. I'm not writing them down here, and then subject to all conditions. This part I will solve for all scenarios. set of scenarios. So once I solve this, I will get, let's say this is maximum profit. So I will get how many profit points. So let's say the profit uh, NW, number of profits. Okay. So this many profits I will get, and they will have certain probability as well, because each scenario has certain probability. In Monte Carlo, generally, like what I have done so far is uh, I created based upon the probability function. I assumed that okay, some value is obtained, and like generally what I did is I had some mean value, I had some variation, and between those mean and variation, I was able to come up with some minimum and maximum value, and I created as many points as possible randomly from that boundaries. So those will give me that okay, these are the different possible values which uh, like if some mean boundary values are there. So let's say if the forecast is 50 megawatt, and it can go up to like the below is like the error is plus minus 10 megawatt. So the range is 40 megawatt to 60 megawatt will be the forecast. Okay. So what we did is randomly created multiple values between that 40 to 60, and tried to solve the optimal value if all those scenarios can be there. So this is how basically, like for each scenario I solved the problem separately, and I was able to obtain the profit, and then based upon the profit I was able to calculate the risk value. Okay, and then the expected value can be calculated. So in Monte Carlo simulation, you just create the scenarios. Now scenario creation is the very brute force approach is randomly create scenarios, like whatever is the value, minimum maximum value, and randomly pick one value, and use uniform probability. Like in this particular example, I have let's say created 10 scenarios, and I'm using the probability of 0.1 with each scenario, that all the scenarios have the same probability of 0.1. Okay, now some of the scenarios can give me a very high profit. Some will give me low profit, and let's say 50 minus 20, then 500, 600, and let's say 900 and 1000. Okay, so these are the different profits are available. By looking at these profits, the probabilities are same. Now if I want to calculate the like if I draw this function, I can say, like instead of this, if I plot some community probability, so profit is here and some probability is here, and these are randomly created. So I can say that I have some minus 20. Okay, and this minus 20 has the probability of zero point 0.1. Okay, then we have which is the next 50. So let's say this is 0 and this is 50. So this has a probability of 2. So I can move here, and probability is 0.2. Okay, this is 0.1. So the community probability will be 0.2, and it also has a probability of, like this is 0.1. This scenario has a 0.2, and so on. Basically, I can draw the further part of the entire curve, and up to it is like I think profit of being 12,000, and the probability will be finally 1. Okay, so let's say the alpha, like we defined value at risk with some alpha, which is called confidence level, and let's say that is 80%. So 1 minus alpha will be 20%. So I will see that at 20%, what is the value of profit. So if you can see with the 20% probability, so this is the 20% probability, and profit values are basically this and this value. So there are two values possible. One is 50 and another one is I think 50 and the next higher value is 150. Okay, so 150 will move away. So for this 20% confidence level, I have different values, and if you see the value at risk is defined at the uh, like probabilities which are less than 1 minus alpha, which is, let's say, in this particular case 20%. So the profit function value which will be less than the neta value, and the probability should be 20%, and what can be the maximum value of neta. So here the neta can be take 50 or 150. So I can define that the value at risk in this particular part is 150. The value at risk is 150, and by looking at this particular value, that the maximum value of neta for which this, so let me copy this one and explain it this particular example so that you will be able to understand it more accurately. Okay, so control C and let me put it here. Okay, so you can check here that the probability of function value less than alpha. So for first of all, the function value is minus 20. So that probability is 0.1 for minus 20. And so I can start with, like different value of neta. So let's say if neta is minus 20, then the condition, like the probability for which this fx is less than neta is only 0.1, and it is less than 20, so that satisfies. So neta can be minus 20, but we have to, like let's say I start with neta equals to minus 20, and if I solve this particular problem, if neta equals to assumed 20, then the probability of functions, so function value xw less than minus 20, neta value is minus 20, and what will be that value, and 1 minus alpha, and alpha is 80%, it is like 20%. So this is nothing but equals to this entire term is equals to 0.1. The probability is only 1% that this function value is less than minus 20, or I think it is 0, sorry, it is 0%, because none of the function value is less than minus 20. So none of the function is less than minus 20. So this neta has to be increased. Now if we increase the neta to the 50 value, then I will see that the function value should be less than 50. So function value less than 50 is only for this sixth scenario where the value is minus 20 and rest of them are above it, and the probability of that is 0.1. So this is 0.1 and this is 20. So yes, it satisfies the condition. So neta can be 50. But if I look at the next part, the next can be like 150. So the neta is 150, and other effects are basically like the which have lesser value is 50 and 20. So these also have the same probability, and the summation of those probabilities are 20. So 20 is less than equals to 20. So yes, that is the final condition which has been met, and the neta will become 150, and that will be the maximum value of neta which provides me this, but satisfy this condition is 150. If I move further away, like let's say consider 300. So for 300, these three values will be lesser, and the total summation of these three probabilities will be 0.3. So the 0.3 is not less than 0.2, which is 1 minus alpha. So 300 can never be the value at risk. So this is how we can calculate the value at risk. Okay. So I think we should stop it here, and thank you. Okay. we will have, I think, tomorrow again the 10 to 12 and 2 to 4 sessions are there. So we will discuss more about optimization and different types of modeling tomorrow. Okay, thank you.